The most useful result in one-dimensional calculus is the chain rule. And so now we want to study what the analog of that is in higher dimensions. And in order to state it, the cleanest way to state it is in terms of matrices. So let me first review those. So an M by N matrix is a rectangular array of numbers with M rows and N columns. So for example, 1, -1, 0, 2, 2, 3. This is an example of a 2 by 3 matrix. And we sometimes write the entries of a matrix like this: A1, 3, A2, 1, A2, 2, A2, 3. So Aij means the ith, the ith row, and the jth column. So a mnemonic for remembering this convention is maybe Roman Catholic is one. I guess ricotta cheese is another, or whatever you prefer. So what we're going to want to do with matrices is take their product. So the definition: if A is an M by N matrix and B is an N by P matrix, then the product AB, so this is only defined, we can't multiply just any matrices, the dimensions have to match up correctly. This will be an M by P matrix whose ijth entry is, maybe the easiest way to say this is the dot product ith row of A with jth column of B. So for example, let's let A equal 1, 0, 1, -2, 1, 3, and B equals B equals 1, 2, 1, 0, 1, 3, 0, 1, 1. So here we have M is equal to 2, N is equal to 3, and P is equal to 3. Then to multiply these, it's convenient to arrange these as follows. So 1, 0, 1, -2, 1, 3. And then we'll put B above here. So 1, 2, 1, 0, 1, 3, 0, 1, 1. And now to find an entry, I multiply across a row of A and down a column of B. So this will get a little bit scrunched, but should only be 2 rows. So we'll do 1 times 1 plus 0 times 2 plus 1 times 1, and that gives us 2. Then in the next one, we'll go 1 times 0 plus 0 times 1 plus 1 times 3, and so we get 3 here. Then we would get 1 times 0 plus 0 times 1 plus 1 times 1, and that'll give 1 here. Then continuing, we get negative 2 times 1 plus 1 times 2 plus 3 times 1, so that gives, the 2's cancel out, so we get 3 here. Then we'll get negative 2 times 0 plus 1 times 1 plus 3 times 3, and so that should give us 10. And finally, we'll have negative 2 times 0 plus 1 times 1 plus 3 times 1 is 4. So the matrix AB will be 2, 3, 1, 3, 10, 4. The motivation for this formula we'll learn in a linear algebra course, but we can just take it as a useful shorthand for writing out these long multiplications. Okay, so now the chain rule. Basically, the chain rule in general, so I'll state it just very generally and then give some examples to demystify it. So let's say we have a function from f from Rm to Rn, which, as we've seen, consists of really a bunch of functions f1, x1 through xm, down to fn, x1 through xm. Then to this we will get an n by m matrix. So beware the codomain corresponds to the number of rows, and the domain corresponds to the number of columns. So we can get an n by m matrix where the entries are going to be, so for one of the particular rows, like del fi over del xj. And then if we have another function, like g, so we call this the Jacobian matrix of f. Let me just write it. J of f. So then G will also give now a P by N matrix del Gi by del xj, or maybe we should call these y1 equals yn equals, so del yj. And so the chain rule for higher variables in full generality says that the Jacobian matrix of the composite G compose F is the Jacobian matrix of G times the Jacobian matrix of F. So there's lots of, for different values of these variables, this translates into lots of different formulas, but this is a succinct general principle. So I know this is very, this is sort of very symbolic and intimidating, so now let me give an example. So, and I'll give lots more examples in the next video, but so let's look at a function R2 to R3, and then another function from R3 to, let's actually go to R2. So I'll call the coordinates here S and T. Here I'll call the coordinates X, Y, Z, and here I'll call them U and V. So let's take X is equal to cos T, Y is equal to sine T, Z is equal to S. Actually, let me put S times cos T, S sine T, Z is equal to S, and then U is equal to X squared plus Y squared plus Z squared, and V is equal to X, Y, Z. So if I call these F and G, then the Jacobian of F consists of the matrix del X by del S and del X by del T. I'm sorry. Jacobian of F consists of del X by del S, del Y by del S, del Z by del S, and del X by del T, del Y by del T, del Z by del T. And this we can see is, okay, so that'll be cos T sine T 1 negative S sine T S cos T 0. Then Jacobian of G, this will be del U over del X, del V over del X, del U over del Y, del V over del Y, and del U over del Z, del V over del Z, which we're running out of space. We can, right, this will be 2x, 2y, 2z, and this will be yz, xz, and xy. So erase, I guess, this part. And so the chain rule is going to tell us that the composites, so if we look at del U by del S, del v by del s del u by del t del v by del t, the chain rule is telling us that this is del u by del x, del u by del y, del u by del z, del v by del x, del v by del y, del v by del z times well, this thing. So if we write that out, I guess we remember what these functions were. Okay, so that is the product. That's going to be the product 2x, 2y, 2z, yz, xz, xy, cos t, sine t, 1, negative s, sine t, s, cos t, 0. Erase this. Right, and so that will be 2x cos t plus 2y sine t plus 2z. And so this is just one entry, so let's split this up. I guess erase this now. Then yz cos t plus xz sine t plus xy. Then over here we'll have negative 2x s sine t plus 2y s cos t, and then the last one 0, and here we'll have negative s y z sine t plus s x z cos t. But then since we can substitute in the values of, so x is s cos t, y is s sine t, and z is s, then this will simplify to, this is 2s cos squared t plus 2s sine squared t plus 2s, should be an s. So this will actually become just 4s. Then down here we'll have, so 2s, I guess this will become 2s squared cos t sine t plus another, or maybe that's 3s squared cos t sine t. Yes, 3s squared cos t sine t. And then negative 2x s, so this will become negative 2s squared cos t sine t, but then plus 2s squared. So I guess this will actually become 0. And then negative s yz sine t. So this will be negative s cubed sine squared t plus s cubed cos squared t. So it'll be s cubed times cos squared minus sine squared. So see what the chain rule is doing. Let's try to go and see this directly. Okay, so our formulas for u and v, so u is if u is x squared plus y squared plus z squared, well, that is going to be s squared cos squared t plus s squared sine squared t plus s squared. So u is equal to 4s squared, and v is equal to x, y, z. Well, that's s cubed cos t sine t. And now we can calculate directly from here that del u by del s is 4s, del u by del t is 0, and del v by del s, well, this is 3s squared cos t sine t, and del v by del t we can see is s cubed cos squared t minus sine squared t using the product rule. And so we get this by a direct calculation, and this is what the chain rule calculated for us in terms of the intermediate partials.